Okay, so previous video we saw how we can use logarithms in solving application problems related to exponential growth. In this video we're going to continue that discussion, moving on to talk about our continuously compounded interest formula. And remember, this applies for all sorts of other things, particularly for population growth to other areas. Uh, like population areas, like population. And we'll look at some different examples here in this, in the rest of the notes here. So let's look at one related to a financial account real quick. So it'll be real similar to the last one. It says if $800 is invested in an account that earns 7% in annual interest compounded annually. Sorry, I meant for that to say continuously. Small typo there. We want to talk about continuous interest here. If $800 is invested in an account that earns 7% annual interest, compounded continuously, how long will it be before the account reaches $2,000? So we want to use our continuously compounded interest formula. Identify the things we know. We want it to reach an amount of $2,000. And we'll start, the principal will be $800. So we start with 800, we want to get it up to 2,000. E is that constant value that we talked about. We don't need to remember that it's 2.72, but it's helpful if you, or it might just be a nice piece to hold on to. So we have that constant growth factor here coming from Euler's number. And then we have our growth rate is 7% annual interest. So we express that as a decimal as 0.07. Then we plug it into our formula here. But t is the thing that we don't know, right? That's what we're trying to figure out. We want to know how long will it take for this to happen. So A is the amount we're trying to get. That's 2,000. P is the amount that we have. That's 800. E is the constant, Euler's number. Our growth rate is 0.07. And t is the thing we don't know. How long will it take for us to get to 800 or to 2,000 from $800? So again, we're just going to use inverse operations, right? Once we kind of get the hang of using logarithms, this really becomes a fairly straightforward process and kind of redundant as we do a bunch of examples. Okay, but we're just using inverse operations, remembering now that the log is the inverse of the exponential function. In particular, we're seeing right here why it's so useful to just always lean on natural log. The rest of our examples that we're going to do in this section are about continuous growth. So they're always going to have this base e. And the inverse of base e is the natural log. And so this is really handy because when I take the natural log of both sides, natural log and base e will cancel each other. And so I'm left with the natural log of 5/2 is equal to, now on the right side, natural log and e cancel, so I'm just left with 0.07t. So it simplifies the computations a little bit for me because it gets rid of that base e. And now I can just divide by 0.07 to get t by itself. And so t will be equal to the natural log of, we'll say 2.5 divided by 0.07. And that's the exact amount of time it will take. If we type that into a calculator to get an approximation, we have, the natural log of what was it? 2.5 divided by 0.07, and we get 13.089 or 13.09. So 13.09, or how about just 13.1? It's going to take just over 13 years for our account to grow from $800 to $2,000. Okay, and we can compute any number of continuously compounded interest accounts like that. So it works for any financial account if we have continuously compounded interest. And other lots and lots of actual real world phenomena are modeled by this natural continuous compounded growth function, specifically population growth. So let's look at a local example for us here. The population of Seattle was approximately 725,000 people in the year 2017, and at that point had been growing for a few years at a rate of 2.46% per year. Population grows continuously. On the Chapter 7 test, that was something that cost a number of people a point or two, was they used the yearly compound interest formula instead of the continuous compound interest formula. Population should always use the continuous formula, okay? Because people are continuously being born. So population is growing continuously, not in increments of once a day the population grows or once a year the population grows. It's always growing continuously. So use the continuous formula. Now, let's see. It says if the population continues to grow at this rate, when will the population of Seattle surpass 1 million people, right? And Seattle, as you well know, is already fairly crowded, and the traffic is not the greatest. So just imagine if we crossed over 1 million people, what it's going to be like in Seattle. Let's see how long it's going to take for us to get there. So it's the exact same function as we did in the last problem. Our principal, though, instead of a certain dollar amount, is the number of people that we started with. So we started with 725,000 people. And we're interested in when will we get to 1 million people, right? And we know that our city's population is growing at 2.46% per year. So as a decimal, always remember to turn it into a decimal. That's 0.0246. Okay. And we're interested in how long will it take for this to happen? How long will it take for 725,000 people to grow into 1 million? Again, population growth is modeled very well by our continuously compounded interest formula. It's the exact same formula as the previous problem. But now we know we have 1 million people. We started with 725,000, and we are growing at 0.0246 per year. Okay. If you're looking at this and saying, can I just drop all these zeros and just say 1,725 and know that I'm talking in units of 1,000, that's fine. Just make sure you, that would be totally fine since we have both of these units both of these are in units of 1,000. So now we want to go ahead and solve for t, but we're just doing the exact same series of operations as the previous couple of examples here. So we want to do inverse operations to isolate the variable. I'm going to divide out the 725,000 on both sides. On here, those zeros all cancel. 1,000 over 725 is not quite 4/3. So we can just leave it as that. We can simplify it down if you want. You're going to put it into the calculator anyway, so I would just save it till the end and do it in the calculator all in one shot. We get 0.0246t as the power on e. And remember, we just talked about this. When we are using logarithms to solve equations, I would encourage you to use natural log always because of how frequently we'll be using e in application. So this is why we spend so much time talking about e in natural log. Is it has so many powerful applications of this kind in all sorts of social sciences and physical sciences, and we'll study it more in calculus. It's a super powerful function for us to use as base e. So we'll take the natural log of both sides because natural log and base e are inverses. They cancel each other. And I'm left with the natural log of 1,000 over 725 equals 0.0246t. I can divide that 0.0246 out. That's going to leave me with t is equal to exactly the natural log of 1,000 over 725 all divided by 0.0246. Okay, if you haven't noticed, this is a very calculator intensive section. So yes, use your calculator. Don't sit here trying to do these operations by hand. Use your calculator. If you want to go piece by piece and figure out what that is and take it as a decimal and then plug that into natural log and take that as a decimal and divide by that decimal, you can do it incrementally if you want. Depends on the capacity of your calculator. if you can type this all in one time and one shot in your calculator, that's what I would suggest. But I know a lot of scientific calculators that can be really tricky. So here we go. Let's go ahead and find out what that actually is in terms of number of years. So we want the natural log of 1,000 divided by 725 all over 0.0246. And that's going to take about 13.1. Hey, very good, similar. About 13.1 years. Okay. So this means, coming back to the context, it's going to take about 13 years for us to reach 1 million people. So 13 years after 2017 is going to mean that this is going to happen roughly in the year 2030, which isn't that far off, only about 10 years from now. If population growth continues to go at the same rate, we could expect Seattle's population to cross 1 million people by the end of the year 2030 or so. And of course, these are approximations. It's worth taking it all with a bit of a grain of salt. It's an approximation. That's a rounded number. It's hard, you can't count every single person in a city as big as Seattle, so that's always an approximation. And our growth rate is rounded, right? 2.46% versus 2.47% could be a significant difference. When you're talking about millions of people, that might be a 10,000 person difference, or the longer you go, could be 10 or 50 or 100,000 people. So small changes in growth percentage could affect this pretty significantly. All sorts of things can affect this. So it's an approximation, but it is fair to say that if Seattle's population continues to grow, as it has been growing in the last 5 to 7 years, then we could anticipate its population crossing 1 million people around the year 2030. And we're going to look at a couple more examples in one last video here in a minute, but there's just 2 quick examples of using the continuous growth function and using logarithms with the continuous growth function to do certain application problems.